Hey guys, welcome back to chapter 13. Now we are going to work an example using what we learned about reaction quotient Q, and then what we learned about predicting where equilibrium was based on that. So here's an example. So consider the reaction and its equilibrium constant. So our reaction is iodine reacts with chlorine to produce 2 molecules of ICl. And in this case, it gives us the equilibrium constant, which is 81.9. So we're doing the experiment, and we reach in, we measure each of the components somehow, and the reaction mixture at this moment contains 0.11 molar of iodine, 0.102 molar of chlorine, and 0.355 molar of the product. Is this reaction at equilibrium? And if it is not, which direction will the reaction proceed? So to solve this, we're going to need to solve first for reaction quotient Q. So just a reminder, Q equals products, concentration, reactants, right? So in this case, if I were to draw a kind of formula for this reaction, I would have the concentration of our products, ICl, and remember the coefficient becomes an exponent, divided by the concentration of our reactants, and now we're given numbers for each of these values, so now we just simply plug them into that equation. So the concentration of our product is 0.355. Once you put numbers in here, you can replace the brackets with parentheses. And then remember that it's squared because of that coefficient. And then on the bottom, we're going to put the concentration of each of our reactants. So iodine was 114. And chlorine is 102. You likely will skip a couple steps in solving this, but I'm going to be very explicit about solving this because I want to talk a little bit about how the units fall out here. So on the top, I'm going to take 0.355 and I'm going to square that. So on the top, we get 0.126, and the units become molarity squared. So we square the units, it becomes molarity squared. On the bottom, I'm going to multiply these two numbers together. 0.114 times 0.102, and the number we get on the bottom is 0.1. Oh, excuse me. 0.01116. Now the units here, we've got molarity times molarity. So the units here also become molarity squared. And the reason this is important is because I've got molarity on top, molarity squared on top. I've got molarity squared on the bottom. Those two cancel. And my Q, and this is also true for K, my Q value will always be unitless, okay? So there are no units. Notice there's no units up here on the K value, and there's going to be no units on the Q value. So that's why I went through that. So now I just plug both of those into my calculator. 0.126 divided by 0.116, and I get a value of 10. So that is my value for Q. That's how I calculate for that. We're not quite finished with this problem. We got a couple more questions to ask. So number one, is this reaction at equilibrium? So in order for a reaction to be at equilibrium, K would equal Q. That is not the case. K is 81.9, Q is 10.9. So no, this is not at equilibrium. Now we have to decide which direction will the reaction proceed. Where is equilibrium? So what we see in this scenario is that Q is less than K. So this is the scenario we're in. Q is less than K. So we could think about this from that graph standpoint, if you liked that. So if this is K right here, we're somewhere down here, which means we would have to go up towards this dotted line to find equilibrium. Or if we think about this as reactants, products, this would have to push towards the products to find equilibrium. So which direction will it proceed? It will proceed towards products. So that's just a quick example of a reaction quotient Q equation, and then also how we relate Q to K. I hope you guys found this helpful.